So myself, Raju, today I'm going to discuss on the control and energy management in microgrids. So this is the outline of my presentation. So I'm going to discuss briefly on the smart grid, and after that I will discuss on the microgrids. In that I will discuss on the classification of the microgrids, operating modes of the microgrid, control of the microgrid, and after that I will discuss on the energy management in microgrids. And finally I will discuss on the what are the challenges, what are the research directions in this microgrid area. So coming to the smart grid, so as we know that smart grid is the combination of the conventional electrical infrastructure as well as the intelligence infrastructure. So when we are combining the conventional power system network with the ICT, information communication technology, then we can get the smart grid. So this is simply called as the energy internet. So how the smart grid is going to help? So with the smart grid, we will have the three objectives thing. One is we can increase the use of renewable energy sources. We can have the better management of the energy uses. We can also improve the electrical power generation distribution. So by integration of the electrical infrastructure as well as the ICT infrastructure. So by integrating the alternating energy resources like solar, wind generation, power storage, so we can also integrate the distributed energy resources into the power infrastructure. So like what we are currently our program. So we can also match the supply and demand to reduce the traditional bulk generation. And coming to the better management in the smart grid, we are going to integrate the smart meters, and we will have the demand response systems. So to reduce the balance between the generation and the demand. So we can also enable the use of the electric vehicles, and we will have the more environmental friendly energy storage and all those things. So if you see the conventional power system network, so we usually have the bulk power generation, after the transmission, distribution, customer, and upon that we have the market operations and also service provider. So when we are moving towards the smart grid, so we will have the high use of the variable renewables, and we will have the distributed generation as well as the microgrid integration at the distribution level, and we will have the more smart meters as well as the real-time usage data, and we will have the bidirectional metering. Since when we are integrating the DZs or the microgrids, so you will have the bidirectional power flow between the grid and the microgrids. So in that case, we need to include the bidirectional metering like net metering, and we will also have the distributed energy storage, and we will have the more smart appliances, so which will work based on the IoT applications, and we will also have the energy management system, and we will have the more integration of the electric vehicles, and we will have the many number of the sensors which will provide the measurements of the all the power system variables. So if you see the evaluation of the traditional power system to the modern power system, so as you can see, so traditional power system is mainly having the conventional power centralized generation, and after that we have the primary transmission, secondary transmission, primary distribution, secondary distribution, and we have the loads. So here we can see we have the unity single power flow direction. And coming to the modern power system network, so we will have the distributed power generation, distributed renewable integration like distributed PV system, and we will have the distributed wind system. So when we see the evaluation of the traditional power system, so as we can see here, we have the bidirectional power flow due to the distributed generation units as well as the microgrids. If you see the conventional one, we have the unidirectional power flow. So when we see the typical line parameters, so if you see high voltage lines usually having the R by X ratio, since X is the dominating, we usually have the 0.31. And if you see the medium voltage, we will have the 0.85. If you see the low voltage lines, we will have the 7.73. So this R by X ratio is very important when we are talking about the microgrid, since we are integrating at the low voltage distribution network, and this R by X ratio is going to play an important role in the microgrid. So coming to the microgrid, so I will discuss about the how we are evolving from the distributed generation, distributed energy resources, and after that virtual power plants, and after that microgrids. So first we will see what are the main motivation behind why we are moving towards the distributed generation or the distributed energy resources. So the main motivation, as we can see nowadays, the power demand is going to be increased very high. If you see the power demand in 2016 of the Indian power grid, if you see this is the motivation I'm discussing here. What is the motivation behind the integration of the distributed energy resources? So it is mainly the first point was increased demand, and after that we are experiencing some electricity shortages. So we are also experiencing some power quality problems. We are also having some blackouts, and also we are having some electricity price spikes because of the different power plant vendors. So due to this, we are moving towards DER integration. So coming to the DER, so DER is mainly defined as a electricity generation unit typically in the range of 3 kilowatt to 50 megawatts. So it is usually located within the electric distribution system or the near the end user. So these can be connected parallel to the electrical grid, or we can also connect on the standalone. So this DER distributed generation is not a new one. So it is available from the many years. So earlier we were calling it as a generators or the backup generators or the on-site power systems. And also we have some different terminology like distributed generation, distributed power, and distributed energy resources. So distributed generation means, so it is the technology that produces only the power outside the utility grid, like we have the smaller power generation like photovoltaics, microturbines, fuel cells. So it is mainly power generation one. When we see the distributed power, so this is any technology that produces the power as well as the stores the power. So now we are combining the distributed generation as well as the distributed power, and also we are also combining the demand response loads. So by combining all these things, we have one terminology like distributed energy resources, which combines DC technology, DEP, and also demand side measures. So under this configuration, we can sold the power back to the grid. So when there is a regulation is permitting. So coming to the distributed energy resources, so as I mentioned, it is small scale power generation. So that is mainly located close to the where the electricity we are using, or it is nearer to the home or business. So it provides the alternative to the centralized power generation. So why we are moving towards the DER is, so it is the faster, it is the less expensive option. So when we see the conventional generation, if you want to build some larger 500 megawatts or the 1 gigawatt power plant, so we have to spend a lot of money and we have to spend a lot of efforts for that. However, when we want to when we want to install the small scale power generation, so it will be very faster and it will be less expensive option, say as compared to the central power plant. And also, since we are integrating these small scale power generation or the DERs at the distribution level, so we can avoid the losses in the primary transmission, secondary transmission, primary distribution, so that we will have the lower cost, we will have the higher service reliability, we will have the higher power quality, increased energy efficiency, and also we also have the energy independence. Like we don't need to completely depend on the centralized power generation, since we have the power generation at the distribution level. So now we can act it as a energy independence. So if we are going with the renewable distributed energy resources integration, then we will have the green powers. Like we can go with the integration of the solar, photovoltaic, and we can go with the wind, geothermal, biomass, hydroelectric. So this will have the one more advantage, that is the significant environmental benefit as well. So these are the different distributed energy resources. So as we can see, so we are mainly classifying the DERs into two types of technologies. One is the DC technologies, another one is the distributed energy storage. So coming to the DC technologies, we have the renewable energy DCs as well as the non-renewable DCs. In the non-renewable DCs, we have the internal combustion, external combustion. So there we have the three types. So in the external combustion, we have the one type. And coming to the renewable DCs, we have the solar, wind, biomass, tidal wave, micro hydro, geothermal. So nowadays, we are also having the hydrogen-based fuel cells. So those are also coming under the renewable DCs. And we have the distributed energy storage. So that is the chemical, mechanical, electrical, thermal, and electrochemical storage. If you see the DCs, if you see the solar DC, solar-based DER, so that produces the DC power, and wind produces the variable AC power. So we cannot integrate these DER technologies directly into the power system. So definitely we need some power electronic interface. So that is what here I'm showing here. So generalized power electronic interface for the integrating the DER into the grid. So as we can see, so DER can produce either the DC power or the variable frequency AC power. And here we have the 4 modules. One is the source input converter module, and after that we have the inverter module. So in order to integrate with the AC power grid, and we will have the output interface module, so like a filter module. So in order to reduce the harmonics, and we will have the monitoring as well as the controller module, so which will monitor all the modules and which will take the coordination action of all the remaining 3 modules. If you see the DERs, so we have included all the DERs like DC technologies as well as the energy storage. So if it is a DC technology, you will have the unidirectional power flow, and if it is a battery, if it is the energy storage system, and you will have the bidirectional power flow. So if you see the PV1, in the input converter module, we have the either AC-DC converter or the DC-DC converter. So AC-DC converter is for the DC technology which produces the variable AC power, and DC-DC converter is for the DC technology or the energy storage technology which is producing the DC power. So these are the different types of the power electronic converters that we are using for the interfacing any DER. So we usually have the 4 types of converters. So AC to DC converters, DC to DC converters, DC to AC converters, and AC to AC converters. So we rarely use the AC to AC converters because of higher number of the switches, and designing the control for the higher number of switches may going to be complex as well as the costly. So that is the reason we always prefer the 3 converters, that is AC to DC converters, DC to DC, and DC to AC. If you see in the down figure, so here I have given the how we are going to integrate the DC based source as well as the variable AC power source. So DC based source can be integrated by using the single DC AC converter, or also we can also include the energy storage. So when we have the variable AC source, we are using the back-to-back AC DC as well as the DC AC converter, and in between the DC link we can also integrate the energy storage. So when we are going for the direct integration of the DC technology into the distribution network, so we are having the different issues. So like we have the issues like when we are going for the modeling of the network components. So when we are integrating the DC technologies, you may have when we are integrating the DER, you may have the bidirectional power flow. So in that case, we may have the issues with the modeling of the networks. So we may have the issues with the power quality. We will have the system stability, and we will have the production issues. Since we have to take care of the each and every unit independently. So in that case, controlling all the components individually is going to be difficult for maintaining the better system stability, production issues, and power quality issues. So here I have given the voltage profile, how the voltage profile is going to affect. So when we are going for the DC integration, so as we can see, we are experiencing the poor voltage profile when we are moving towards the low voltage distribution lines. So this is because of the resistance value, R by X ratio, and resistance value domination of the low voltage distribution network. So in order to avoid all these issues, so we are moving towards the microgrid concept. So as we can see, microgrid includes the DC and energy storage technologies, and we can also include the backup generators and UPS power supplies, and we can also include the DR management system. We can also include the virtual power plant. So when we combine all these things, we will have the one network, small scale network, that is called as a microgrid. So as we can see, we have some advantage, we have some benefits with the DC integration. Also, we have some issues with the DC integration. So instead of controlling all the DCs independently, so it's better to combine some few DCs. So then we can have one small scale system. Then we can integrate that system into the grid. So that would be the better way how we can get the benefits of the integrating the DC units, as well as the overcoming the issues with the management of all the DC network components independently. So the word microgrid, if you observe the word microgrid, so we have the 2 words. One is the micro, another one is the grid. So micro, it's mainly providing the extremely small attribute from the grid point of view. And when we see the grid, it is having the network of the electrical lines. So therefore, so microgrid will have the small scale power system network. So which is having the generation and distribution and load. So we will not have any transmission like in the conventional power system network. And you will also have the control of all the DC units. So without creating any complex network. So this is what are the microgrids. So as I mentioned, microgrid can be the low voltage distributed system or the medium voltage distributed system. It is having the distributed generation. It will have the storage devices. It will have the critical as well as the non-critical loads. It will have the communication. It will have the control and automation system. It will have the production devices. It will also have in the smart connecting switches. So it can be operated either in the islanding mode of operation or the grid-tied mode of operation. So by operating the static switch at the point of the common coupling, so where we are connecting the microgrid with the utility grid. So here we can see, so from the definition, we can say that it is a small scale power system network. So having the generation, storage, having the loads and well established communication, control, all these things. So it is like a lower scale, small scale power system network with well established control, automation, production, each and everything. So it can be act as a controllable source or the controllable load from the grid point of view. So when we have the higher power generation in the microgrid, it can be act as a controllable source. So when we have the more power demand and within the microgrid, it can be act as a controllable load. So that you can control the entire microgrid community as per the mismatch between the power generation as well as the demand. If you see the microgrid barriers, so we have mainly regulatory as well as the administrative barriers. In that we have many barriers like technical barriers, infrastructure barriers, economic barriers, financial barriers, public acceptance. So there are many barriers to make the microgrid as a real practical one. So this is how the microgrid architecture look like. So as you can see, we will have the renewable energy sources, we will have the conventional generation resources, so we will have the energy storage system, we will have the integration of the electric vehicles, so we will have the smart buildings, we will have the smart homes, and we will have the grid connection, and also you will have the weather forecasting. If you see the solar, PV and wind, so these are mainly dependent on the weather conditions, so you need to forecast the weather, so in order to control the power generation output from the PV as well as the wind, and you will also have the energy market. So in this you can see every component will have their own local control, and that will be connected to the microgrid central controller. So these are the main components of the microgrid. So we have the distributed energy resources. So that is the combination of the DG technologies as well as the energy storage as well as the demand response load something. And we will have the loads. In that you will have the critical as well as the non-critical loads, and you will have the smart switches, you will have the protective devices, we will have the master control, that is called as a MGCC, microgrid central controller. You will have the control, you will have the control and automation, and you will have the communication. So I am going one by one, I will go by one by one. So when we see the DE, as I mentioned, it will have the DG as well as the energy storage. So DG technologies can be dispatchable as well as non-dispatchable. So dispatchable means DG technologies for which we can control the output, those comes under the dispatchable, and DG technologies for which we cannot control the output, that comes under the non-dispatchable. If you see the solar, PV, wind, so for that output is dependent on the weather conditions and we cannot control the output, so those comes under the non-dispatchable. So when we see the conventional energy sources like micro turbines or the IC engines, so those comes under the dispatchable for which we can control the output. And when we have the renewable energy resources, so these are mainly weather dependent, and these are mainly intermittent resources. So for that we should have the presence of the energy storage system. So why we are going for the energy storage system is, so we need to go for the load leveling, that is the matching between the generation as well as the load demand. So with that you can have the frequency regulation, and we can also have the energy arbitrage. So energy arbitrage means like exporting the power when we have the high rates, importing the power when we have the low rates of the energy cost. So likewise we can have the more profit from the microgrid. So this is the classification based on the according to the size. So we have the 5 classification, like we have the micro DES, mini DES, small DES, medium and large. So when we see the micro, so if any DER having the power rating, power generation less than 2 kilowatt, that comes under the that comes under the micro. So that will be always considered the low voltage network or the single phase network. So the typical example is the rooftop solar PV. And when we see the mini, so that comes in between the 2 kilowatt to 10 kilowatt. So that can be, if it is a single phase, that comes under the 2 to 10 kilowatt. If it is a 3 phase, that comes under the less than 30 kilowatt. So for example, fuel cells, combined heat and power systems. So when we see the small scale, that comes in between the 10 to 30, and 3 phase, three phase, for 3 phase only. We will see when the DER having the higher power rating, so we usually go with the 3 phase integration. So when the DER having the lesser power rating, we are going with the single phase connection. If you see the micro one, so we should go with the single phase connection only, and mini one we can go with the either single phase or the 3 phase. Coming to the small, medium, large, these should be connected at the 3 phase level only, like medium voltage distribution network or the low voltage 3 phase distribution network. So this is the comparison between the various types of the DERs. So as we can see here, I have given the dispatchable resources as well as the non-dispatchable. So as I mentioned, in the dispatchable, we have the CHP, diesel backup generator, gas generator, fuel cell, micro turbine. So coming to the non-dispatchable, we have the photovoltaic, hydro, wind turbine, tidal. And energy storage technologies, we have the different energy storage technologies. So when we see the non-dispatchable, so these are the clean energy resources, and there will not be any cost for the power generation. So when we see the dispatchable, so these will provide the continuous power dispatch. However, these are having the multiple fuel options. However, these are having the greenhouse gas emission. These are not clean resources. So when we see the non-dispatchable or the renewable sources, so we have the clean power generation. But the problem is you will have the fluctuations in the power generation, and also these are expensive as compared to the dispatchable one, since these are all related to the geographic locations. So when we see the loads, we have the flexible loads as well as the non-flexible loads. So we have the fixed as well as the flexible one. So flexible loads means these are the variable loads, so that can be shifted, that can be curtailed, and this can be also called as a controllable as well as a non-critical loads. So when we see the fixed loads are the non-controllable loads, so we have to supply the power continuously without any interruptions, irrespective of the any grid failures. So like when we are having the hospitals, when we are conducting some online exam in our university, so we have to produce the power continuously without any interruption. So for that we need to, those are comes under the fixed loads. So these are the different types of the energy storage technologies. So as we can see, we have the main types: mechanical, electrochemical, thermal, electrical, hydrogen based one. So this is the nowadays recent trend. So in the mechanical, we have the different types like pumped hydro, PHES, so gravity storage technologies, compressed TIES, flywheels. So likewise, we have the different classification in the energy storage technologies. So we can go with the different energy storage technologies based on the application. If you see here I'm giving the application based on the time scale. So time scale here, the short, medium as well as the long. If you see here, for the short scale, we can go with the supercapacitor or the superconducting magnetic energy storage, and flywheels also can be used for the short term energy storage. So when we see the medium term, we have to go with the batteries, electrochemical energy storage. For the long term, we have to go with the pumped hydro, compressed air. That means these are the energy storage technologies based on the time scale, means that provides the power for the how much time will produce. So here I have given the discharge time at the rated power as well as the system power rating. So as we can see, if it is the power rating in terms of the hundreds of the megawatts, 1 gigawatts, so we can go with the grid scale power storage, that is the pumped hydro or the compressed air storage. So these comes under the long-term energy storages. So when we see the transmission and distribution, there we can go with the battery technologies. So when we see the UPS or the power quality applications or the less power rating, less discharge time, in that case we have to go with the high power flywheels or the high power supercapacitors. So this is the energy storage applications. So this is mainly based on the matching between the power generation as well as the demand. So whenever we have the surplus power, so we can utilize the excess power for the charging. So whenever we have the power deficit, we can discharge the batteries to to make the frequency constant steady state value. So here we can see the frequency variations as well as the charging and discharging power related to the frequency stability. So likewise load leveling also we have the same. Like whenever we have the higher more loads, so in that case we are going for the discharging. Whenever we have the lower load, then we are going for the charging of the batteries. So likewise we can have the optimal utilization of the energy. We will also have the smart switches, production devices. So smart switches mainly manage the connection between the DES and the loads in the microgrid. So by connecting the disconnecting line flows, so like we will have the smart switches. So in case of the any fault, we have to separate the microgrid from the main grid. So for that we need the smart switch in between the microgrid and the main grid. So we will also have that smart switch also will perform the islanding of the microgrid. So that can be the either intentional islanding or the non-intentional islanding. So we will have the MGCC master controller. So that mainly performs the scheduling of the microgrid. So in the grid connected as well as the islanding mode of operation, so that we have to meet the economic as well as the security constraints. So it will also determines when we have to interconnect microgrid with the main grid and when we have to disconnect the microgrid with the main grid. And it will also make the decision between the whether we will go for the islanding mode of operation or the grid connected mode of operation. It will also manages the optimal operation of the local resources. And after that we will have the communication control automation. So all these required for the effective as well as the reliable interaction among the microgrid components. So these are the various communication technologies that are used in the microgrid. So as we can see, when we this figure gives the data rate as well as the coverage area. So when we are going with the more coverage area, then we have to go with the more data rate. So likewise, we can decide the based on the microgrid on which in which square area it is occupied. So based on that, we can go with the what type of the communication technology. So these are the different benefits of the microgrids. So since we are moving towards the more renewable integration, so that we can reduce the greenhouse gas emission, and we can also reduce the transmission as well as the distribution cost. Since we are integrating at the distribution level, so we can reduce the cost of the primary transmission, secondary transmission, primary distribution, and we can also reduce the losses from this primary and secondary transmission. So we can also improve the reliability by introducing the self-healing capability. So as I mentioned, microgrid can be acting as a controllable source or the controllable load. So it can manage on their own, so that it will have the self-healing capability. And after that, since we are managing the critical loads by providing the continuous power supply, so that we can maintain the better power quality, and you will have the higher flexibility and controllability as well as the efficiency of the operation. Since we are controlling the microgrid as a single unit, and you will also have the bidirectional power flow between the microgrid and main grid. So whenever we have the surplus power, that surplus power will be exported to the main grid. So whenever there is some power requirement in the microgrid, so we can import the power from the main grid. So likewise, you will have the bidirectional power flow between the main grid to microgrid. So you will have the flexibility, and also as I mentioned, you will have the power supply to the critical leads without any interruption during the main grid failures. And also you can disconnect the microgrid from the main grid when there is some voltage fluctuations or when there is some disturbance in the main grid. So these are the different benefits of the microgrids. So here I am going with the classification of the microgrid. So we can classify the microgrid based on the different points. So when we see the types of the generation sources, so we can classify the microgrid. So type of the distribution also we can classify the microgrid, like we can also classify based on the what type of the operation modes we are taking. So we can also classify the what type of the control strategy we are going with. So here I am giving the complete classification of the microgrids. So we are mainly classifying based on the location, based on the application, based on the distribution system. So based on the location, we can classify into the urban microgrids as well as the remote microgrid. So based on the distribution, we can classify into AC microgrid, DC microgrid, hybrid AC DC microgrid. And based on the application, we have the power type, supervisory control type, we have the operation mode type, we have the phase type, we have the application type. So power type, we have the AC and DC, and supervisory control, we have the centralized as well as the decentralized. In the operation mode, you may have the islanded, only islanded microgrid or the isolated microgrid, and you may have the both islanded as well as the grid connected, and you may have the single phase and three phase. So based on the how much watt scale DERs you are integrating with the system, so likewise we can go with the either single phase or the three phase. And also based on the application, whether we are going for the residential application or the utility application. So likewise we have some different classification of the microgrids in the literature. So here we are giving one classification, that is based on the power distribution, that is the AC microgrid, DC microgrid, and hybrid AC DC microgrid. So if you see the AC microgrid, we have the common AC bus, and in the DC microgrid we have the common DC bus. So DC technologies are the energy storage. If you see the photovoltaic PV panels, so that produces the DC power, and to connect with the AC bus, we are using the DC AC converter interface. So when we see the wind turbine, that produces the variable AC power for connecting with the AC bus with the constant frequency. So we are going with the AC-AC converter or the back-to-back AC-DC converter, DC-AC converter. For the energy storage, we are integrating with the DC-AC converter. And when we see the load side, if it is the AC load with the same voltage, we can directly connect it to the AC bus. If it is a different voltage, then we have to go with the AC-AC voltage controller, or maybe we can go with some other converter. And if it is the DC load, we are going with the AC-DC converter. So here we can see in the DC microgrid also same, like whenever we are having the, we are connecting the DC source with the DC-DC converter, AC source with the AC-DC converter, like load also. So as we can see, there are some multiple power transmission, multiple power conversions. So when we see the power conversion from the photovoltaic panel to the DC load, so there is some DC to AC conversion, again to DC to DC conversion. So this involves the multiple power conversion. So that causes the multiple power losses in the system. So in order to reduce all those multiple power conversions, so we are going with the hybrid AC-DC microgrid. This is a hybrid AC-DC microgrid. So here we can see, so we are connecting the sources, loads, which are producing the AC power, which requires the AC. So those are connecting to the AC bus, and also sources which produces the DC power, which requires the DC power loads. So we are connecting the DC bus. So in between the AC and DC bus, we have the bidirectional AC-DC converter, and we are having the main converter as well as the backup converter. So when there is a failure in the main converter, we can go with the backup converter. So here I am giving the comparison between the AC and DC microgrid. So if you see the conversion efficiency, so ACMG involves the multiple energy conversions, as I mentioned in the earlier figure. So that mainly causes the reduction in the efficiency. When we see the DCMG, in the ACMG, it involves more AC-DC converters. In the DCMG, it involves more DC-DC converters. So you will have the less conversion process, so that we can increase the efficiency. So when we see the transmission efficiency, in the AC microgrid, you will have the continuous reactive current loss. So that causes a reduction in the efficiency. In the DC microgrid, there is no any reactive component, so we can increase the efficiency. So when we see the stability, in the AC microgrid, the stability is mainly affected by the external disturbances, and coming to the DC microgrid, it is free from the external effects. So when we see the synchronization, AC microgrid needs the synchronization, and DCMG doesn't require any synchronization. So when we see the power supply reliability, so since the conventional power distribution network is the AC one, so you will have the so here the power supply reliability supply can be affected by the any from grid mode to islanding mode to grid mode. But coming to the DCMG, we have the reliable power supply. So when we see the control in the AC microgrid, you have to control the frequency as well as the voltage stability, so that the complex control is going to be complex. And coming to the DCMG, we have to take care of only the voltage, and in that you may have the simple control approach. And coming to the production, so we already have the well established production for the AC, but we don't have the production for the DC. So that is the reason when we see the DCMG, we have the complex production, we have the costly as well as the immature production. When we see the ACMG, we already have the major technology for the production system, but however, DCMG, we are not having any major technology for the production system. So when we see the suitability, so ACMG is more suitable for the AC loads and DCMG is more suitable for the DC loads. But when we see the conventional distribution network, AC distribution network, so nowadays we all are having all the AC interconnection only, all the AC loads only, although inside we may have the AC DC converter, something DC load, but when we see the point of connection, so we have the AC distribution connection only, so all are the AC loads. So when we see the calculation methods, so AC microgrid usually includes the impedance calculations, so we will have the complex numbers. So when we see the DCMG, it only have the resistance, so you will have the real numbers which are used. So this is how the hybrid AC-DC microgrid looks like in the real. So here we can see the same thing, like we have the AC distribution, so we have the DC distribution. So in between we have the bidirectional AC-DC converters and we have the switch for disconnecting the AC and DC microgrid. So here I am giving the summary of the AC-DC hybrid AC-DC microgrids. So as you can see, so we have the advantages, we have the disadvantages of the AC and DC microgrid, and we also have the we are taking the advantages of the AC microgrid, DC microgrid with the hybrid AC-DC microgrid, and we also have some drawbacks with the hybrid AC-DC microgrid. Like we need to go for the complex design, and we will have the more stability as well as the production challenges, and we will also this hybrid AC-DC microgrid may not be the practical for the rural electrification as well as the isolated communities, since the system is a complex one. And also when we see the implementation cost, this hybrid AC-DC microgrid involves the higher cost in the implementation. So likewise, we have some disadvantages with the hybrid AC-DC microgrid, although we have some advantages with the hybrid AC-DC microgrid, like we have the better harmonics control, better frequency synchronization, and we have the excellent voltage conversion support likewise. So when we see the concept of the multi-microgrid, here we can see the n number of the microgrids are connected to the distribution network through the transformer of the distribution transformer through the grid. So this is how the multi-microgrid connection looks like. So I am going to give on the isolated as well as the non-isolated configuration here. So non-isolated means, so as we can see, we have the microgrid. On the top of the microgrid, we have the central controller. So on the top, we have the utility grid connection. So in between, we have the transfer switch as well as the distribution transformer. So this non-isolated grid means that can be operated. So this can be operated both in the grid connected mode of operation as well as the islanding mode of operation. Also, there is a mode transfer between the islanding to grid connected mode of operation. So there is a point of common coupling or the point of connection in between the utility grid and the main grid. So this is a non-isolated grid. So when we see the isolated one, so here we can see there won't be any connection for the grid. When we see the isolated areas or remote areas, so there we will not have the access of the distribution lines. So we will not have access of the grid. So in that case, we can go with the isolated microgrid, having all the microgrid components as well as the microgrid central controller. So the main difference is here we don't have any. Here we have the access of the distribution power grid. We have the access of the main grid. So we will have the connection of the main grid. So here we don't have the access of the main grid. So here we don't have any point of the connection for the main grid. So if you see the operating modes, so when we see the non-isolated microgrid, so that can be operated both in the grid connected mode of operation as well as the islanding mode of operation. So when we are operating in the grid connected mode, so it will be act as either controllable source or the controllable load. So that means it will simply follow whatever the active and reactive power references, so that are given by the main grid. So the DES and other components will simply follow what are the requirements by the utility grid. So when we see the islanding microgrid, so microgrid itself has to take care of the frequency and voltage stability, and they have to generate the frequency and voltage references. So in that case, what we are doing is, so we may go with the generating the voltage and frequency reference with all the DERs, or we may go with the generating the voltage and frequency references with at least one or the group of the DERs, and that will provide the voltage and frequency references to the remaining DERs. And we should have the load tracking, and we should have the load management, we should have the load shedding, so in order to maintain the match between the generation as well as the demand. And also you will have the many stability issues like transient stability issues, since if there is any loss of the DER, if there is any sudden change in the load, you will see the large spikes, large variations in the frequency and voltage. So in that you will see the transient stability. So coming to the mode transfer from the grid to islanding mode. So it's mainly divided into two types. One is the intentional islanding as well as the unintentional islanding. So intentional islanding means we are going to isolate the microgrid from the main grid intentionally by monitoring the parameters like voltage, frequency, and all those things, and what is the power flow between the main grid to main grid. So unintentional means when there is some failure. So when there is some failure in the main grid, then we have to go for the islanding of the microgrid with the main grid. So this is the control of the non-isolated microgrid. When we see the grid control mode of operation, so as I mentioned, you have to control the active power as well as the reactive power. So as I mentioned, microgrid will be acting as a single source or the single load. So when we see from the point of the common coupling, so when we see the control of the active power, since simply we have to control the active power flow to the utility grid. When we see the reactive power, we have some different control of the reactive power. So we have the constant power factor control, we have the fixed reactive power control. So we have the reactive power control as a function of the active power. So we have the reactive power as a function of the voltage. We have the reactive power as a function of the active power as well as the reactive power. And also it involves the control of the internal resources as well as the other loads in order to achieve the objectives of all these active and reactive power control. So coming to the control of the isolated microgrids, so here we have to observe the what is the control of the islanding mode of, we have to see the difference between the control of the microgrid, non-isolated microgrid in the islanding mode of operation and control of the isolated microgrid. So when we see the control of the non-isolated microgrid in the islanding mode of operation, so that control is completely different from the control of the isolated microgrid. Since isolated microgrid means there won't be any option, from the main grid. Then the microgrid itself has to take care of the each and everything. So when we see the power quality of isolated microgrid also, we have to take care of the each and everything, and we have to take care of the voltage and frequency control. When we see the control strategies for the voltage and frequency, so these will be different from the whatever the voltage and frequency control we are using in the islanding mode operation of the non-isolated microgrid. So these things completely different. So when we see the non-isolated microgrid, in the isolated microgrid there won't be any option of the grid. So everything should be controlled from the whatever the resources available in the isolated microgrid, whatever the control available in the isolated microgrid. So here I am giving the microgrid control general architecture. So as we can see, we have the three levels in the control. So one is the primary level control, secondary level control, and tertiary level control. So when we see the primary control, so it's mainly a local control of the DER units. So that is having the power converter. So we are simply controlling the power converters. So when we see the secondary control, so that is mainly related to the energy management system. So when we see the tertiary control, so this control is taken by the DSO operators or the distribution network operators or the market operators. So here I am giving the more detail in the coming slide. So here I am giving the control hierarchy. So as we can see, we have the primary level control, secondary level control, tertiary level control. So these three controls are different the speed of the response. So these are the different the time frame in which they are operating. So they are also different the communication infrastructure. So coming to the primary level control, it is called as a local control. So it's usually having the voltage and current control. It will have the power sharing control or the power control based on the islanding mode of operation or the grid control mode of operation. So when we see the secondary level control, so it is mainly when the primary control is not able to maintain the voltage and frequency within the voltage and frequency oscillations within the limits, then the secondary level control will come into the action, and that will go for the voltage and frequency restoration. And also if it is a grid connected mode of operation, then we are going with the power flow and synchronization control. So that is mainly acting for the power quality control. So when we see the tertiary level, so in this we have the generation forecasting, we will have the microgrid supervision, we have the economic dispatch as well as the operation. So these three controls are different in the speed of the response and time frame in which they are operating. They are also different in the communication infrastructure. So when we see the primary level control, so this doesn't require any communication, much more communication. So when we see the secondary level control, it requires a communication infrastructure. So when we see the tertiary level control, it requires a more communication infrastructure as compared to the secondary level control. So here I am giving the in which time frame they are working. So as we can see, primary control will work on the tens of the milliseconds, and secondary control will work on the hundreds of the milliseconds, and tertiary control will work in the seconds to minutes. So inner loop control, it may have the voltage and current loops, and primary control, you will have the local control, loop control or the power control. In the secondary control, you may have the voltage and frequency restoration control, or the load management, or the automatic generation control. In the tertiary level control, we have the economic dispatch as well as the unit commitment as well as the voltage VAR control. So here also I have given the same thing. If you see the primary one, so it is acting in the tens of the milliseconds. So in that we have the frequency and voltage control as well as the power sharing control. So that is mainly for the power quality. So when we see the secondary control, island detection will also comes under the secondary control, power dispatching as well as the thermal comfort. So when we see the tertiary one, we have the forecasting of the generation, we have the demand response, we have the economic dispatching as well as the electricity market. So if you see the time frame, primary is coming in the tens of milliseconds to seconds, and secondary comes under the seconds to minutes, tens of milliseconds to seconds, and tertiary coming under the minutes to the hours or the days based on the whatever the task we are going to do. So this is how the microgrid control looks for the when we are dealing with the multi microgrids. So as we can see, every microgrid having their own secondary control, and all these secondary control are controlled by the tertiary control or the main level distribution system operator. So here I am giving the microgrid control one by one. So there are 4 levels. So one is the level 0, level 1, level 2, level 3. So level 0 comes under the inner control loop. So that involves the current control, output voltage control, feedback or the feed forward compensators. That includes the linear, non-linear control techniques. So when we see the local control, it comes under the primary control. So that usually involves the power sharing control like group control methods or the virtual impedance control methods or the power control in the island grid connected mode of operation. So when we see the secondary level control, we have the MGCC like microgrid central controller. So that mainly communicate with all the local control of the DERs, and that will take care of the voltage and frequency restoration. So when we see the level 3, it comes under the global control. So it is mainly manages the power flow between the within the microgrid, and also power flow between the one microgrid to another microgrid based on the generation forecasting and other variables. So this is the example for the inner control loop. We have the voltage and frequency control. We have the, so this is upper one is for the islanding mode of operation. The lower one is for the grid connected mode of operation. So when we are dealing with the inner current control loop. So here I am giving the one example. So here I have given the one distributed generation which is taken for the islanding mode of operation. So as we can see, we have the control section, we have the power processing section. So in the local control section, we have the power sharing controller, voltage controller, current controller. So in the power processing section, we have the inverter, we have the LC filter, coupling inductor. So inverter responsible for converting the DC into AC, and LC filter responsible for mitigating the harmonics, and the coupling inductor responsible for matching the impedance of the DC as well as the microgrid, main microgrid bus. So when we see the control techniques, control section, we have the power sharing control. It is the outer loop one, and voltage and current control. This comes under the inner loop control. And in the second picture, I have shown the same inner outer loop control for the rectifier interface active load. So here I am giving the more detailed. So as we can see, when we see the inner controls, voltage and current control is there. So here I have shown the DQ axis voltage and current control. And then in the second figure, in the down figure, I have shown the power sharing controller based on the Droop conventional Droop 1. So this is how the primary local Droop control we are implementing. So there is, as we know that we have the well-established Droop control for the conventional synchronous generation. So the only thing is like when we are using this Droop control for the conventional power transmission, their X by R ratio is different, and here X by R ratio is different. So because of the R by X ratio, because of this R values, X values, so here the Droop control may not be that much effective as compared in the transmission. So we will have some issues, and I will show with one example. So what are the issues we are going to face? So when we are implementing this Droop control or the decoupling control with the distribution network. So here how we are giving the Droop selections to all the primary level control. So as we can see, we are taking the total power demand. So we are taking the what is the generation dispatch from the other generators, all these things. And based on that, we are going with the Droop selection, and we are giving the Droop values for sharing the total load demand across all the generators based on their proportional power sharing. So here I am giving the one example. So I have taken the one microgrid having the four distributed generators, and we are also having the all different types of the loads, like we have the induction motor load, we have the constant power load, and we have the rectifier interface active load, and we have the resistive load. So first I have taken the equal power ratings, and after that I have taken the unequal power ratings. And equal power, based on that we have given the Droop gains. So if it is the equal power rating, so total load will be shared by all the generators equally. And if it is the unequal power ratings, so the power load demand will be shared by all the generators based on their power rating proportionally. So in this figure I am showing the how that power is going to be shared. So in the upper figure that shows for the equal power ratings. So as we can see, so after 5 seconds power generation from all the generators, we are getting the same. And coming to the second down figure, so as we can see, we got the unequal power rating, we have the unequal power rating, and we have the unequal power sharing between all the generators. So in this we can see DC1 having the lowest power rating, and DC2 having the DC4 having the highest power rating, and we have taken the increasing from the DC1 to DC2. So likewise, in the second figure, you can see how the power is going to be shared among all the DCs. So in the first figure, in the down figure, we have given for the unequal power sharing. In the first figure, we have given for the equal power sharing. So when we are taking for the equal power ratings or the equal Droop gains, so as we can see, we have the equal active power sharing, and we have the frequency scheduled at after 5 seconds. So however, we can observe that so reactive power is not sharing equally, although we have the equal power ratings. So when we see the second figure, we have the proportional power sharing as per the power rating of the DCs. And coming to the reactive power, still we have the problem with the reactive power sharing. So this is mainly due to the R by X ratio, whatever I have mentioned in the one of the slides. So when we are dealing with the distribution network, so we have the R by X ratio is very high, and this power decoupling may not work. So there may be some coupling between the active power and the voltage, and reactive power and frequency. So because of that, Droop control is not working effectively for the reactive power sharing. So here I am giving the one more primary level control. So there we are having the master and slave control. So master inverter will generate the voltage and frequency references, and that voltage and frequency references will be given to the slave one, and those will generate the whatever the active and reactive power required by the loads. So likewise, we will have the master and slave control. So next we are going with the secondary level control. So as we can see, secondary level control is mainly aiming for what are the shortcomings with the primary level control. So when the primary level control is not able to mitigate the voltage and frequency deviations within the limits, so then we are going with the secondary level control. Then the secondary level control will come into the action, and it will go for the minimizing the voltage and frequency oscillations. So as we can see, if you see the secondary level control, we have the frequency reference value, and we have the frequency of the microgrid, and we are taking the difference between the frequency reference and frequency of the microgrid, and with that we are with the PI control we are going to minimize the frequency and voltage deviation that will be given to the whatever the local level control. So there are some different control techniques for the secondary level control. So there are some different control techniques for the secondary level control. So that is the decentralized control, centralized control, distributed control, as well as the hierarchical control. So I will go one by one. So coming to the decentralized control, so we have the, as we can see, we have all the DC sources having their own primary control. So upon the primary control, we have the secondary control individual. So however, so there is no communication between the secondary control of the all the individual primary control. So because of this, there is a lack of the uniformity as well as the consistency, and there is no coordination between the secondary control of the all this decentralized control. So coming to the centralized control, so we have the primary control of the all the DC units. There is a one secondary level control. So in between we have the communication infrastructure. So this communication infrastructure will communicate all the primary controls with the secondary control, so that they will have the coordination of all the primary control with the secondary control. However, so if there is any failure of the communication infrastructure, then there is no communication between the secondary and the primary control. So because of this, this is suffering with the single point failure. That means, so when the communication is going to be failed, then there is no any secondary control action from the secondary level control. So when we see the distributed control, so earlier in the decentralized control, so we don't have any communication between the secondary control. So here we have all the secondary level control, they are communicating with each other. So they will have the proper coordination, and they will have the proper control for the secondary level control. So when we see the hierarchical level control, so we are simply combining the decentralized control as well as the centralized control. So as we can see, upon the primary control of all the DC units, all the DER units, you will have the secondary control, and upon that you will have the centralized secondary control. So in between you have the communication infrastructure. So even though if there is any failure with the communication infrastructure, still we can maintain the minimum stability with the secondary level decentralized control. So there is also one more higher. Here I have given all the controls in the one figure. So as we can see, we have the decentralized control, we have the distributed centralized controller. So by combining the centralized as well as the decentralized one, you will have the hierarchical control. So there is also one more control we can get from the combining the hierarchical control as well as the distributed control. So if we combine the distributed control and the centralized controller, then you will get the hierarchical distributed control. So that would be the one of the future research topic which we can work for the better control of the microgrid. That is the hierarchical distributed control. So that combines the centralized control as well as the distributed control. So here I have given the comparison between all the different controls. So as we can see, centralized control, it is mainly having the strong observability as well as the controllability, and we have the straightforward implementation. So however, it is suffers from the single point failure. So this is preferable when we are going with the localized area or the small size MGs. So for example, we can go with the master slave control. So when we see the decentralized control, it is the simple control one, since we are implementing at the decentralized level. So it is a decentralized one. So it is also independent from the digital communication technology. With the less communication technology, we can implement the decentralized control. So what are the main problem is we have the limited performance due to the shortage of the information. As I mentioned earlier, there is no coordination between the different secondary level decentralized control with the other secondary level decentralized controller. So that causes the accuracy problems, also some other control issues as well as electrical parameters. And coming to this decentralized control area does not require, and we can pass the information with the decentralized control. The best example for the decentralized control is the group control. So coming to the distributed one, so as I mentioned earlier, in the distributed, we have the communication between all the secondary controllers with the other controller, so that it is immune to the single point failure, as well as it can be feasible to interact with the other units through the communication lines. So the only demerit is the when we are going for the more communication, we have to go for the more investment on the communication infrastructure, as well as we have to manage the data from the all the communication devices, and we have to coordinate that data with all the coordinates of the different DC units. So for the battery energy storage system, we can go with the distributed control. The best example is the coordinated control. So when we see the hierarchical control, so it is the combination of the centralized as well as the decentralized control, or the centralized as well as the distributed control, hierarchical distributed control. So it is mainly reliable and economical when we are going for the standalone microgrids or the standalone DC units. So here also we have the demerit is the main thing is the complexity when we are going for the control structure, as well as when we are going for the hierarchical. You may have the communication requirement at the decentralized level, and you may have the communication requirement at the centralized level, so that you will have the complex communication. So when we are going for the complex modern system, then we can prefer the hierarchical control. So the best example is the agent-based control is the best example for the hierarchical control. So this is how the global control looks like. So as we can see, we have the global control, we have the secondary control, and we have the primary control. So here we can see in the global control, simply we are getting the active and reactive power references from the microgrid operating manager. So with that active and reactive power references, we are generating the frequency and voltage references, and those will be given to the secondary control. And secondary control will give the what are the voltage and current references for the primary control. And based on that, we will have the coordinated operation of the all the DERs as well as the DERs, including the DC units as well as the local controllers. So this is the global loop control. So this is how the microgrid real-time control looks like. So as we can see, we have the 3 layers. So one is the operational layer, another one is the prediction layer, another one is the external layer. So in the operation layer, as we can see, we have the centralized controller. So that is going to be communicate with all the local control of the power electronic converters. And after that, this centralized control is going to communicate with the prediction layer. So this prediction is very important when we are dealing with the renewable energy resources. So like we have to predict what is the solar radiation, what is the wind speed for the next minutes or the next seconds or the next hours or the next day. So like that we have to predict all the variables. In the external layer, we have the weather conditions as well as we have the human machine interface. So here we can see we have the power flow as well as we have the bus line, we have the information flow. So as we can see, when we are going for all the different layers of the control, we should have the proper communication between the prediction layer to operation layer as well as the external layer to the prediction layer. So this is another illustration. So as we can see, we have the operational layer, we have the energy management layer, we have the prediction layer, and we have the human machine interface. So this HMI will provide what is the end user demand, and after that the prediction layer will provide what is the solar forecasting data as well as the wind forecasting data, and after that we have the energy management layer. So that will provide what is the power PV prediction and what is the load prediction, and that will give to the operation layer. So based on the prediction of the PV power, based on the prediction of the load and prediction of the other generation. So likewise, we can give what is the active power reference of the PV, active power reference of the grid, and active power reference of the storage, active power reference of the diesel generator, and also what is the load constant, how much load we can maintain. So like that, you will have the real-time control. So this is one more thing, the same thing I'm showing in the more detail. So as we can see in the end user demand, so we will have the load shedding limit, we will have the building criteria applications, we will have the operation criteria. So there we have the human machine interface. So with that you can provide the whatever the end user commands, and after that you have the weather data as well as there we can see we have the load forecasting data, we have the load shedding program, we have the weather forecasting data, we have the load scheduling as well as we have the time of the use prices, we have the grid peak hours. So likewise we have all the data. So from that we will get what is the predicted load for the next short term or the long term or the medium term. We will have what is the power generation from the PV, wind, and other resources, and we will also have what is the state of the charge of the battery for the next short period, medium period, long term period. So likewise we will send the active and reactive power reference to the operational layer. So these are the different control methods that we are using for the stability enhancement. So we have the conventional control methods, like we have the linear quadratic control, we have the sliding mode control, we have the PID control, droop control, model predictive control, and PSO based control. So like all the control having their own advantages as well as the disadvantages. So when we see the types of the connection, so LQC can be applied both for the grid connected as well as the islanding mode of operation. So when we see the PID control, that can be applied only for the islanding mode of operation. And when we see the droop control, other controllers can be applied both for the grid connected as well as the islanding mode of operation. And also you can see that where we can apply this control technique for the renewable energy sources as well as the grid other sources or the synchronous generators. So when we see the LQC, that can be applied for the renewable energy sources as well as the grid control. So when we see the droop control, that can be applied for both the synchronous generators as well as the renewable energy resources. So, and also we can see at which voltage level we can apply these control. And if you see the droop control, we are usually prefer to apply at the higher voltage level, since you will have the lower R by X ratio and you will have the less decoupling, and this in that case droop control will be more effective in that case. So when we see the other control techniques, those can be applied at the medium voltage levels or the high voltage levels. So these are some different optimal control strategies. So as we can see, when we say the optimal control strategies, means we are going to combine the control technique as well as the optimization of the any objectives. So here we can see we have the optimization of the objectives, and we will utilize the. So when we are talking about the optimal, then we have to go for the what are the different optimization techniques. If you see the optimization of the objectives, you may have the economic as well as the environmental objectives. You may have the power flow objectives. So when we see the economic and environmental objectives, you may have the energy dispatch, demand side management, economic dispatch, carbon dioxide emissions. So when we see the power flow one, so we have the optimal power flow and load shedding. So when we see the optimization techniques, we have the different types of the optimization technique. You can go with the any optimization technique based on your application, whichever is providing the better results for that particular application. So with this, I have completed the control strategies. So I will go with the energy management. As you can see, we have the variable sources, we have the loads, and we have the energy prices. And on the right side, we have the energy import and export, and we have the DER control, we have the demand side management. So energy management strategy, it's mainly controls the power flow in the microgrid by adjusting the what is the imported power, what is the exported power from the different components, like what is the imported power, exported from the power from the main grid, and what is the power import, export from the dispatchable DERs and controllable loads. So these three are the main from which we can control the power output, and we can manage the power import as well as the export. And all these things are the based on the what is the present information of the market, and what is the forecasted information of the market, and also what is the present information of the generation as well as the loads, what is the present information of the variable sources, what is the forecasted information of the variable loads. So like we will see all the components for which we can control the output, import or the export. So for which we will see all these things, and we are going to, at the end of the day, we're going to control the what is the power flow in the microgrid by adjusting all these import and export powers. So at the end of the day, we have the one objective. So that is we have to minimize the cost of the operation. So for that, we are going for all these controls. So these are the different objectives in the energy management strategies. So as we can see, we can take any of these objectives. So based on our target. So as we can see, we have the objectives like greenhouse gas emission cost. We have the objectives like operational maintenance cost of the energy storage system. We have the leveraged cost of the energy of the renewable energy resources. We have the operational maintenance cost of the conventional generators. So we have the energy transaction cost. We have the battery degradation cost. We have the outages as well as the interruption cost. We have the demand responsive incentives. We have the losses cost. So we have the load shedding penalty cost. So we have the different objectives that can be taken in the energy management strategies. And we also have the many constraints. So like we have the network constraints, we have the physical limits of the energy storage system. So we have the physical limits of the conventional generators. So we have the reliability constraints, we have the reactive power support constraints, we have the demand response constraints. So we have the output limits of the renewable energy resources, energy balancing. So like we have the many constraints, and based on our target, based on our particular application, so we can go for the selecting the different objective functions. So we can go for the selecting the different constraints, and we can go for the minimizing the one or two objective functions by taking the different constraints. So these are the here I am showing the functions of the energy management system. So as you can see the flow, we have the data monitoring of the all the available elements in the microgrid. As we can see, we are going to monitor the data of the renewable energy resources. We are going to monitor the data of the conventional generators, energy storage system, demand response, electric vehicles, grid, import and export from the grid. And also we are going to monitor the data of the weather forecasting. So after capturing the data, after monitoring and capturing the data of the all the data from the all the different elements in the microgrid, for which we can control the output, so that will be that data will be analyzed. So that is the reason nowadays the big data analytics is one of the trending research topic in the coming research areas, since we have the big amount of the data from the different resource elements, and we have to do the proper data analysis, big data analysis, from which what data we can utilize for the proper data we can utilize for the forecasting. So if you don't have the proper data analytics as well as the proper thing, we cannot provide the good data for the proper data for the forecasting. So after the forecasting, we have the optimization. So as we can see, this hierarchy, if you have the proper data monitoring, then you can go for the proper data analysis, then we can go for the proper forecasting. So then we will have the optimization. So there will be some bidirectional interaction with the energy market, and after that you will have the real-time control. So if there is any problem in the data monitoring, if there is any problem in the data analysis, data analytics, if there is some lack of efficiency in the forecasting, then the optimization as well as the real-time control, so all these are going to be affected. So that is the reason nowadays big data analysis as well as the forecasting, and after that optimization, so all these are interrelated, all these are important for the proper energy management of the microgrid, or the proper energy management of the main power system network. So here I have given what are the different goals and objectives of the EMS in the microgrid. So as we can see, we have the three goals. One is the three objectives. So one is the optimization, another one is autonomy, another one is the reliability and resiliency. So when we combine the optimization and the autonomy, you will get the minimization of the cost. So when we see the intersection of the autonomy as well as the reliability resilience, you will have the balance as well as the quality. So when we have the intersection of the optimization as well as the reliability and resilience, you will have the restoration. So these are the different goals and objectives of the energy management system in the microgrid. So here I have given the what are the different objective functions in minimizing the cost of the microgrid. So as we can see, we have to minimize the operation cost, we have to minimize the environment cost. So in the operation cost, you have to minimize the cost of the fuel, you have to minimize the cost of the fuel cell or the maintenance or the capital cost. So when we see the environment cost, you have to minimize the carbon emission, we have to minimize the penalties of the emission. So likewise, we have to minimize the environment cost. So when we see the energy storage cost, we have the charging, discharging, life cycle. Like we have to see what is the we have to maintain proper life cycle, otherwise the batteries are going to be degraded, and for that we have to minimize the energy storage cost. So likewise, we have to consider the these three costs when we are going for the proper energy management of the microgrid. So we have to minimize all these costs. So here I am showing the microgrid EMS. So as we can see, so on the left side we have the grid side utility, weather forecasting as well as the third party service provider. So on the right side we have the customer side. So we have the two sides, one is the grid side, another one is the customer side. So in the grid side you have the utility, you have the weather forecasting, we have the third-party service provider. So on the customer side, we have the renewable energy sources like PV and wind turbine, and we have the non-renewable sources like combined heat power, diesel, and also we have the storage like battery. We also have the electric vehicle interface. So when we see the microgrid EMS, we will have the interface between the grid side. We will also interface of the customer side. So when we see the microgrid EMS, so it's mainly monitoring the controlling all the DERs as well as the loads for the optimal operation. It will also interact with the various DERs, loads as well as the external system for the utility information as well as the weather forecast. So here we can see there are mainly 4 functions. So one is the forecast, another one is the data analysis. After that we have the optimization. After that we have the HMI human machine interface. So here I am going to discuss one by one for that microgrid EMS. So here, as I mentioned, we have the 4 functional requirements. So one is the forecast, another one is the optimization, another one is the data analysis, and after that we have the HMI. So here I am discussing the first one, that is the forecast. So we have to forecast the what is the generation, what is the load, and what is the market. So we have to do the DERs forecasting, we have to do the forecasting of the loads, and we have to do the market forecasting. So we can perform the forecasting in the different scales. So it can be the short scale, it can be the medium scale, it can be the long term. So I will show all those things in the coming slides. So what is the short term forecasting, and what is the medium term forecasting, and what is the long term forecasting. So in the forecasting, we are going to utilize what is the historical data and what are the other inputs. Like historical data means like what is the previous historical data of the weather forecasting for the last 1 year, for the last previous month or previous day or previous time. So likewise, we will take the other inputs as well, corresponding to the loads, corresponding to the market. And also this forecasted data will be used as inputs for the optimization. So if you are not maintaining the accuracy of the forecasting, so then definitely that data is going to be utilized in the optimization, and that is going to be affected. So that is the reason why we need to maintain the proper accuracy of the forecast. So that is the crucial for the EMS, and also that is the crucial for the balancing the supply as well as the demand in the microgrid. So however, so when we see the forecasting, so forecasting is the most challenging thing when we are dealing with the renewable sources. So these renewable sources are the intermittent and the inherent intermittent intensity. They are also having the variability. So as we can see the PVs and wind turbines, we cannot utilize what is the historical data of the last 1 year, since we don't know that how was the weather condition for the yesterday and today's. So like that, it also depends upon the temporal, that is related to the time, and we also have the uncertainty in the controllable loads. So that is the reason why the forecasting is the one of the most challenging thing in the microgrid when we are dealing with the renewable energy resources. So there are different various forecasting methods in the literature. I will discuss those things. So here I am giving the generation forecasting. So as we can see, we are mainly dealing with the renewable energy resources. So these are mainly the weather driven resources. So all these are having the variability ranges from the minutes to hour to year. Like we have the minutely ranges, we have the hourly ranges, we have the yearly ranges. So because of this instability of the renewable resources, we will have the many voltage fluctuations as well as the frequency fluctuations. So due to the mismatch between the active and reactive power generation and the demand, so that will cause the obstacle for the maintaining the power system operation as well as the planning and power system operation. Similarly, when we see the electricity consumption, so it is always completely different. When we see the seasonal wise, so in the winter season, we may have the less electricity consumption. So in the summer season, we may have the more electricity consumption. And also nowadays, climate is changing a lot, and we cannot predict that whatever we are having the seasons for the last year, those are going to be changed for the present year. So that is the reason why this forecasting is going to be challenging thing in the nowadays scenario. So thus we need to develop the appropriate forecasting technique to predict the power generation as well as the load demand. So those are mainly significant when we are going for the supply and demand mismatch issues. So here I'm giving the different forecasting time horizons. So as we can see, based on the whatever the energy management we require, when we are going for the short-term energy management, when we are going for the very short-term energy management, medium-term energy management, or the long-term energy management. So when we see here the very short-term energy management, so that can be the from seconds to the half an hour. When we see the short term, that can be the half an hour to the 6 hours, and medium term 6 hours to the 1 day, and long term 1 day to 1 week. If you see the all these energy management based on the different time frames, so we are utilizing for the different applications. So when we see the very short term forecasting, so it's mainly aiming at achieving the dynamic control for the renewable power generators as well as the load tracking. So when we see the short term forecasting, so it is mainly used for the scheduling the energy flow among the power resources, loads and storage devices. And when we see the medium term and long term, so it is mainly for the price settlement, load dispatch as well as the midnight scheduling. So here we can see, so all these are related to the whatever the hierarchical level control we have taken in the previous slides. So like we have already discussed the primary control, secondary control, tertiary control. So very short-term forecasting can be used for the primary control, and short-term forecasting can be used for the secondary level control, and medium-term, long-term can be used for the tertiary control objectives. So likewise, we can have the different hierarchical level, and with the hierarchical level, we can go for the different time frame forecasting techniques. So here I have given the what are the different forecasting techniques available in the literature. So as we can see, we have the single model based forecasting technique. We have the hybrid model based forecasting technique. So in the single model based technique, we are going to utilize any one of the technique. In the hybrid model technique, we are going to combine the any two techniques. So if you see the single model, so in that we have the AI techniques, we have the parametric techniques. In the parametric techniques, we have the statistical methods and we have the Kalman filter. So in the AI techniques, we have the SVM, fuzzy logic, ANN. Like we can go for the any other AI techniques as well. So in the hybrid model, as I mentioned, we are going to combine any two single models. In the hybrid, we are one is combining ANN with the wavelet, another one is combining ANN with the fuzzy logic, another one is combining the ANN with the SVM, ANN with the genetic algorithm. So likewise, you may have the other hybrid models like combining the any two single models for forecasting the for going for the different forecasting techniques. So here I am showing the forecasting system with the physical hardware. So as we can see, I have already mentioned earlier, we have the operation layer, we have the prediction layer, we have the actional layer. So in the prediction layer, we are going for the forecasting. So that will be forecasting parameters will be given to the centralized controller. Centralized controller will generate all those references for the local control of the different distributed energy resources. And after that we have the external layer. There we have the HMI and we have the weather conditions. So that weather forecasting, that data will be given to the prediction layer. So likewise, we will have all the energy management forecasting system with the physical hardware. So here I am going to discuss another functional requirement. So that is the optimization. So initially we have the forecasting. So once we have the accurate forecasting, so those forecasting variables can be given to the inputs as the optimization. So coming to the optimization, we have to take the when we are going for designing the better EMS algorithm, so that must be able to make the control decisions to optimize the power flow in the microgrid by adjusting the dispatchable DERs and controllable loads, power import export from the grid by minimizing the cost of the operation. So we have the different optimizations, so that can be performed at the different applications. So if, whether we are going to perform at the energy power management, we are going to perform at the demand response, so we are going to perform at the coordinated EV charging, or we are going to perform at the V2G. So likewise, we have the different optimizations that can be performed at the different applications. And also these applications are typically formulated as a non-linear optimization. So why we are going with the non-linear means we are dealing with the non-linear behavior of the renewable energy resources, and we will have the different non-linear optimization problems. And also we have the extensive algorithms that are proposed for the energy and power management. We also have the algorithms for the demand response. We have the coordinated EV charging and V2G in the microgrids. So these are the different optimization techniques that can be utilized in the microgrid EMS. So as we can see, we have the linear, nonlinear programming, and we have the meta-heuristic, we have the multi-agents, we have the dynamic programming. So we have the stochastic and robust programming, and we have the predictive control, we have the artificial intelligence and other techniques. So we can also go for the other optimization techniques. So whichever is applicable for that particular application. So here I am given the what are the different methodologies that can be utilized for the microgrid EMS. So as we can see, we have the mixed integer programming based one, dynamic programming one, nonlinear programming, stochastic method, artificial intelligence. And the mixed integer, we have the linear programming, nonlinear programming, and we have the quadratic mixed integer programming. So in the artificial intelligence, we have the many different artificial AI techniques, like we have the different meta-heuristic algorithm, genetic algorithm, particle swarm observation, fuzzy logic, neural networks. So likewise, we can go for the different methodologies based on our application. So whichever is suitable, we can go with the different methodologies. So here I have given the comparative analysis of the different optimization techniques. So as we can see, all the optimization techniques, they have their own advantages, they have own their drawbacks, disadvantages. So when we see the AI-based one, they usually provide the AI-based techniques that can be utilized whenever there is a quick evaluation of the learner target function is necessary, or maybe we can go fuzzy logic can be utilized when we want to analyze the decision of the system. In which case fuzzy logic will provide the best solution. And coming to the PSO, that usually provides the good results when we are dealing with the scattering and optimization problems. Like genetic algorithms, like we have the dynamic programming. So like we have the different advantages for the different optimization techniques. So we also have the drawbacks, like when we see the neural networks that requires the high computational power requirement. So when we see the fuzzy logic, we may not have the capability of the learning which neural networks have. And when we see the PSO, you may have the complicated computational requirements. So likewise, with the conventional techniques as well as the advanced techniques, we have the advantages as well as the drawbacks. But however, so we can go with the requirement as per our particular application. So here I am going to deal with the another functional requirement, that is the data analysis as well as the human machine interface. So after doing the forecasting, we will have the better variables, and those variables will be given to the optimization. And after that, we are going for the data analysis as well as the HMI. So once we have the data monitoring, we will have a lot of the bulk amount of the data, and we have to analyze the data, whichever is best suitable for the particular optimization or the particular developing the particular tool. Suppose when we are going for the development of the any artificial neural network tool, so we have to decide what are the best power system variables, so that can be utilized as inputs for that particular artificial neural network tool, and we have to do the proper data analysis from that large amount of the data. So here the data analysis, so as I mentioned, so EMS usually collects the huge amount of the data from all the DES, from all the controllable loads as well as the market. So and after that, we have to analyze the data, and we have to provide the insights to better understanding what are the different behavior characteristics of the energy resources. So based on the data, we have to analyze we have to understand we have to provide the better understanding of what is the behavior of the different energy resources, what is the behavior of the different loads, and what is the different behavior of the markets. So likewise, that can be improved. So if we have the better data analysis, so once we have the better all the power system variables, so that can improve whatever the forecasting, whatever the optimization models. So as I mentioned in the first one of the slides, so this forecasting as well as the optimization mainly depending upon the data analysis. So data analysis, we will have a large amount of the data, and from that large amount of data, so we have to do the proper data analysis that can be utilized for the forecast and optimization. So once if we have done any mistake in the data analysis, and that will lead to the wrong forecasting, and that will lead to the wrong optimization, and that will lead to the wrong operation of the all the remaining operational layer elements. And further, we will have the human machine interface. So as we can see, there should be some interface between the machine as well as the human. If you see when we are dealing with the IoT device, when we are connecting the IoT device with the mobile, so we can say it as a mobile as a one HMI device. So from that mobile, you can connect that IoT device at a particular location. Suppose when we are going to monitor the solar PV radiation, and we have the IoT connecting with that pyranometer, so that will be connected to the mobile applications. So this mobile can be act as a HMI, and you can monitor the data, whatever the data of the solar irradiation from that pyranometer, and that is connected to the IoT, and we can also control the what are the parameters for the particular. So likewise, we must have the HMI for real-time monitoring as well as the control of the microgrid, so that we can monitor all the parameters from that HMI panel, and we can also take the control actions through the IoT connecting devices. And also HMI is also provides the interface for the microgrid operator as well as the interact with the other modules of the EMS. So as I mentioned, so it will monitor and control all the parameters inside the one microgrid. It will also communicate with the microgrid operator as well as interact with the other EMS modules in the other microgrids. And also furthermore, instead of the using the large amount of the raw data, so we have to provide the better means of the data visualization as well as achieving of the data. So likewise, if you use all the large amount of the data, it's maybe difficult to monitor all the data. So for that, we have to select the whichever is the best applicable for the data visualization, and we have to achieve the remaining variables. So likewise, it will allow the more customer interactions. So next one is we have the unified communication interface. So as we are dealing with the many different types of the devices, like we have the DERs, so we have the cooling devices, we have the loads, and we have the grid operator. Like all these are having the different communication protocols. So all these are operating at the different communication things. So for that, we need the unified communication interface in order to keep all on the same bench. So like there are mainly two types of the interfaces. So one is a connection interface, another one is a device interface, as shown in the figure. So when we see the connection interface, so it's mainly manages the connection with the device or the gateway. So when we see the device interface, so that mainly manages the communication with the device. If you see we have the many devices. The devices may be operating with the IEEE 61850 communication standard. Some device may be operating with the TCP/IP. Some may having the BSNet. Some may having the DLMS. So likewise, we have the different communication protocols for the different devices. But at the end of the day, we have to bring all these on the common communication interface. That is the unified communication interface. So for that, we have the unified communication interface based on the connection interface as well as the device interface. So for the connection interface, we usually have the gateway. So for the device interface, we usually have the device status, measurements, control, as well as the history that I will discuss in the coming slide. So here we can see there are 4 types of the interfaces, so that must be implemented at the status, measurement, control. So here I have mentioned in the device interface, we have the status, control, measurement, history. So those I am going to discuss one by one. So here we have the status, measurement, control, and history. So when we see the status interface, so that usually provide what is the current status information of the particular inverter, what is the state of the charge of the battery, what is the inverter status, whether it is the on condition, whether it is the off condition, so whether it is operating in the PQ mode of operation or the grid tied mode of operation, whether it is operating ironing mode of operation, like droop control mode of operation, or some other control mode of operation. Likewise, it will also provide what is the system status, so whether the system is a good condition or some failure condition. So likewise, we have the status interface. That status interface will provide all the information of the information related to the status of the different devices in the system. So coming to the measurement interface, so it mainly provides what are the current values measured by the device. So when we see what are the main power system variables, if you see the voltage, frequency, and what is the active power, reactive power, and what is the power factor. So this measurement interface will take care of, will provide the all the current values that are measured by the device, like all the power system variables like voltage, frequency, active power, reactive power, power factor. So coming to the control interface, so it's mainly take the control commands. It's mainly issues the control commands or the control signals to the device, so is that whether the device has to turning on or the turning off, whether we have to set the value. Suppose when we are implementing the droop control, you have to set the droop values. So when you are implementing the PQ reference control, you have to set the active and reactive power frequency values. So likewise, if we suppose when we have the controllable loads, when we are trying to match the generation and the demand, in that case, we can go for the turning on and turning off of the controllable loads. So likewise, we will have the control interface for that particular issuing the control signals to the particular devices. And after that, we have the history interface. So it's mainly provides the what is the historical data of the particular device. So when we see the weather forecasting device, so it's usually provides the historical data, and that we need to interface with the history interface. So as we can see, we have the different interfaces like status interface, measurement interface, control interface, as well as the history interface. So likewise, we have to bring all these things on the one real device using that can be protocol and technology supported by the devices. Like we have to bring the one single interface that is the that can be communicated with all the devices with the different protocols as well as the different technologies that can be supported by the device. So here I am giving the what are some commonly used industrial protocols and standards. That includes, if you see the IEC 61850, so it is mainly for the DL devices. So when we see the DLMS, device language message specification, it is mainly for the smart meters. So when we see the DALI, digital addressable lighting interface, it is mainly for the lighting. So when we see the building automation control network, so BAC net communication protocol, it is mainly for the heating, ventilation, air conditioning, HVAC applications, heating, ventilation, and air conditioning applications. So when we see the OBIX protocol, OBIX stands for the Open Building Information Exchange. It's mainly for the building automation and other proprietary protocols by different vendors. So by using the unified communication interface, by using that one, we can manage all these different communication protocols, and we can communicate with all the devices, and we can exchange the information between all the remaining things, and we will have the extensibility of all these devices. So here I am giving the different types of the energy management schemes. So energy management schemes are, as I mentioned, it's mainly important for the proper operation of the microgrid, both in the grid connected mode of operation as well as the standalone mode of operation. As I mentioned, it mainly determines the what is the output power voltages of the each DC source, what is the output of the load, controllable loads, what is the market analysis, like that. So we are mainly classifying the EMS schemes into the based on the two different things. One is the communication based scheme, another one is the communication less scheme. So when we see the communication based scheme, so in this we are so we in this system information is communicated to determine the what is the operating point of the each DC. In the communication less, we are not going to utilize any communication interface, any communication devices in that. So we are simply go for the decentralized one that I will show in the coming slides. In the communication based one, so we have the centralized energy management scheme as well as we have the decentralized energy management scheme. So in the centralized energy management scheme, so we have the one control center, so that will determine the operation points of the DCs. So in the decentralized, so we have the controllers, so that are connected to the communication bus, and we have the data among all the DC controllers. So when we see the communication less scheme, so when suppose when the communication is going to be too difficult, or when we are feeling that communication is too costly for the DC unit, so in that case we can go for the communication less energy management scheme. So in this case, each and every energy resource will have its own controller without having any communication link with the other controllers. So I will show all these schemes one by one, and I will explain. So here we have the communication based scheme, that is the centralized energy management scheme. So here we can see we have one supervisory energy management scheme, and that is communicating with all the local controllers of the DC units, and we have the utility grid connection, we have the load units, and we have all the forecasting of what is the import export for the grid, and what is the load forecasting, different load for the particular day, and we will have the what is the power generation from the different DC units. So likewise we will have all the variables, and from that we will communicate with the supervised control energy management, and that will communicate with the local controller, and will provide the reference values for the local controller, and from that, so we will provide the reference values for the inner controller of the DC unit. So likewise, so we can have the coordinated operation of the energy management. So this is the centralized one. So in the decentralized one, so as we can see, there is a communication between the local controller, each local controller of the each DC unit. So in the earlier one, so this looks like the centralized control. That is the reason why we are saying it as a centralized energy management system. So here we have the communication between the each and every local control. So this looks like a distributed control, and this can be called as a decentralized energy management scheme. So in this, there is no any centralized supervisory management. So all the local controllers will have their own supervisory energy management, and they will communicate with the other local controllers, and they will take care of the optimal operation of the entire microgrid. So here I am showing the communicationless energy management. As we can see, this simply looks like the decentralized control without any communication. So here we can see the whenever we are feeling like communication is too expensive, or communication is not required for the particular DC unit. Suppose whenever we are dealing with the utilization of the no communication, in that case we can go for the energy management by taking the control variables of the local control of the different units, and we will try to manage the optimal operation of the utility grid. But out of all these schemes, this centralized one is the most effective, and after that decentralized one, and after that this communicationless is less effective as compared to other things. So coming to the implementation of the microgrid EMS. So as we can see, here I have implemented whatever I have discussed in the earlier slides. So in the grid side, we have the automated demand response, we have the market information, we have the weather forecast. So in the customer side, we have the smart submeters, we have the smart appliances, we have the EVs, PVs, and battery. In the energy management, we have the forecast. In the forecast, we have to forecast the DER load, we have to forecast the market. So in the optimization, we have to go for the energy scheduling and demand response. So in the data analysis, we have to go for the historical data and forecast data. In the human machine interface, we have to go for the real-time control as well as the data visualization. So this is the complete overall illustration of the whatever the EMS I have discussed so far in the previous slides. So this is a decentralized system structure. So as we can see, so we have the different devices. So different devices have their own communication protocols, and we have the energy service interface. Here we can see we have the different devices. When we see the DERs, it has the communication protocol like I61850. So when we have the HVAC, we have the DLMS. So likewise, we can see we have the different devices, and we have the different communication protocols. So in between, we have the common communication interface. So that will bring all the different devices with the different communication protocols into the one common communication interface. And we have in between, we have the energy service interface that brings the one common communication interface. And upon that, we have the database, and we have the energy service module. And after that, we have the demand response automated server. So there we are communicating with all the devices, and we are taking the information from all the devices. So we are taking the monitoring of the data and data analysis of the data, and after that forecasting of the complete data, utilizing that analyzed data for the forecasting, and after that optimization, after that giving the reference to all the other devices. So this is how it looks like in the real time. So when we are having the different devices, different communication protocols, and how the energy management system looks like from the DSO operator side. So here I am showing the same thing, microgrid real-time control with some more detail. So as we can see, in earlier I have mentioned, we have the operation layer, we have the prediction layer, and we have the upon system layer. Likewise, as you can see, Here we have taken the sources like PV source, and we have taken the grid connection, we have taken the energy storage, we have taken the controllable DC load. So in the operation layer, as we can see, we have the SOC estimation measurement, and after that we are giving the PV control. So here we can see, so initially we have the forecast subsystem, and after that we have the economic dispatch layer, and after that see here also we have the human machine interface, and from that we can monitor the variables, and we can supply the what are the control variables for the optimization algorithm. And in the operation subsystem we are giving the whatever the constants are obtained from the optimization algorithm. And after the operation subsystem we are giving the what is the power generated by the PV, and what is the power import export for the grid connection, and what is the charging power from the batteries, charging, whether it should be go for the charging or the discharging. And also we have the load, when the loads are going to be on, when the loads are going to be shuttered. So likewise we will have all the coordination. So next I am going to discuss on the different challenges as well as the research direction. So here we can see there are some different challenges in the microgrid, from the energy source side, from the smart load side, from the cyber security side. When we are moving from the smart microgrid, so we have the cyber security issues, cyber security challenges. So when we are going for the more integration of the smart meters, smart controllers, and when we are going for the more IoT devices, so in that case we will have the large amount of the data, and this processing of the big amount of the data is one of the challenges in the implementation of the practical implementation of the microgrid. And coming to the energy resources, we have the different types of the energy resources. So that can be the natural gas based one, that can be the renewable energy resources, and we have to capture so we have to take care of the different integration of different energy resources. And coming to the smart loads, and we may have the battery storage, we may have the smart homes, smart buildings, and we may have the integration of the electric vehicles. So likewise we have the different areas, so where we have the challenges in the microgrid. So in the coming slide I will discuss all these issues. So here I am discussing the stability and other key issues of the microgrid. So if you see the microgrid stability, so microgrid stability is different in the grid connected mode of operation as well as the islanding mode of operation. If you see the grid mode of operation, so we have only the voltage stability. Frequency is taken care of the main grid. So when we see the islanding mode of operation, so in this case we have to take care of the frequency as well as the voltage. So that is the reason we have the frequency stability as well as the voltage stability. So when we see the analysis methods of the stability, so based on the disturbance, so we can classify the stability into the small signal disturbance stability and large signal disturbance stability. So if it is a small signal disturbance stability, we can analyze using the linearized model, since the disturbance is the small, and we can linearize the model. However, so when we are dealing with the large signal stability, so we cannot linearize the models. In that case, we have to analyze the stability with the non-linearized models. So when we see what are the reasons for the small signal disturbance, so we have some different, as I mentioned, in the inner loop control, we have the different feedback controllers, and those feedback controllers may causes the small signal disturbance stability. And small load changes also create the small signal stability, and also we have some power limits when there is some sudden decrease in the power from the DCs. So in that case also it creates the small signal stability. And coming to the large signal stability, when we are taking the non-isolated microgrid, so we may have the different operating modes like islanding mode of operation, grid mode of operation. So when we are moving from the one mode to another mode, so we may have the large signal disturbance and large stability problems. So when there is some loss of the DCs, we will have the large difference between the power generation as well as the power demand. So that creates the large signal stability. So when we have the large load changes, that also creates a large mismatch between the generation and the demand. That will create the large signal stability, and also faults. So these are the main things which causes the large signal stability. So when we see the mitigation procedures, so where we can work, and if we see the small signal disturbance issues, we can use the energy management system to mitigate the small signal disturbances. We can go for the development of the supplementary control loops. We can go for the development of the stabilizers for the DCs. We can go for the coordinated control of the DCs. And coming to the large signal disturbance, we can go for the see, like loss signal disturbance is mainly caused from the loss of the DC or loss of the load changes or the different operating modes or the faults. So if you include the energy storage, so we can simply, if you go for the energy storage having the more power density or more energy density, we can simply mitigate the mismatch between, we can simply minimize the mismatch between the generation and the load. So with that, we have to go with the control of the single energy storage or the control of the hybrid energy storage. Or maybe we can also go with the load shedding methods, from which we can set the controllable loads or the flexible loads or the non-critical loads. And from that, we can maintain the matching between the generation and the demand. And we can also go with the production device setting for mitigating the large disturbance issues. We can also go for the control of the powertronic devices when we are going for the DCMG large signal stability. And furthermore, here I am discussing the other issues with the microgrid. So as we can see, there are some different issues. So coming to the low inertia, so as we can see, we are mainly dealing with the renewable energy resources integration. So when we are, as I mentioned in our previous slides, we are integrating all the resources. What are the distributed energy resources? We are integrating through the power electronic converter. So when we are integrating all these DERs with the power electronic converter, so there won't be any inertia contribution from that particular DER. So we will have the low inertia. So when we have the lower inertia, we may have the higher rate of the change of the frequency, and for the small distance also we may have the faster dynamics. And when we see all the DERs, these are interfacing with the power electronic converters. That means power electronic converters are having the faster dynamics when we are comparing with the synchronous generators, and we will have the more frequency deviations. As I mentioned, when we have the low inertia, so we have the higher frequency changes, we have the higher rate of change of the frequencies. With that, we have the frequency deviations. With that, we will have a lot of the stability issues. So when we see the uncertainty, so as we are dealing with the renewable generation, so when there is a problem with the prediction of the power generation, we may have the uncertainty because of the power generation, because of the power demand. So for that, you may have the generation side uncertainty as well as the demand side. With that, we have to go with the proper energy management. So as I mentioned in one of the slides, so when we see the R by X ratio of the low voltage line, we are having the very high values. So with that, power coupling is the problem. So when we have the higher R by X ratio, we cannot implement whatever the power decoupling techniques we are implementing with the transmission. Like as I mentioned in one of the slides, so when we see the active power sharing, we have the proper active power sharing. However, we don't have the proper reactive power sharing. So that causes the stability problem as well as the reliability problem as well as the economical things. So when we see the operational mode transfer, when we are dealing with the non-isolated microgrid, so we have to go for the seamless transfer between the islanding mode to grid mode to islanding mode. So there is some large distance from the islanding mode to grid mode and grid mode to islanding mode. So in that case, we will have the stability issues. And also we have to work on the proper islanding detection. So when we have to island the microgrid from the main grid, when we have to go for the mode transfer from the grid mode to islanding mode and islanding mode to grid mode. So when we are moving towards the smart infrastructure, then we have to go with the cyber security with the smart devices. And coming to the bidirectional power flow, this is mainly one of the important thing. So although the bidirectional power flow is one of the benefits of the microgrid, but because of this, we will have the reverse power flow, and with this we have a lot of the production challenges, a lot of the voltage variations with that bidirectional power flow. And coming to the regulation policies, we have to develop the regulation policies for the bidirectional power flow things, bilateral transactions. So all these things when we are going for the microgrid implementation. So when we see the power electronic side, so we are, as we can see, we are integrating all the DERs with the power electronics. So when we are dealing with the power electronics or the non-linear power electronics loads, so we have to deal with the harmonics and we have to deal with the power quality problems. So when we are having the more non-linear loads, and we have to deal with the more stability issues. So when we are dealing with the power electronics, like when we are dealing with the power electronic converters, so we have to go for the dynamic modeling of the generators, dynamic modeling of the power electronic interface loads. So in that case, we have to go with the fault current limit, we have to go with the control systems, we have to go with the stability of the control systems. So likewise, see, as we can see, we have the many areas in which we can work in the different issues of the microgrid and the proper implementation of the microgrid. So here I am giving the production issues. So as we can see, one of the main benefit with the microgrid is the bidirectional power flow. But with this benefit, we have the issues with the production. So that is the main thing. So when we see the when we have the grid connected mode to islanding mode, so we have the bidirectional power flow. So with that, we have the when we are moving towards the more PE based interface generation, and you will have the low short circuit capacity, low fault levels, and that creates a lot of the production issues. So likewise, we can work on the different production. We have the different production challenges like fault level current variations due to that more PE integrated distributed generators, and we have to go for the standardization of the production protocols, and we have to go for the choosing of the appropriate transformer configurations for this bidirectional power flow, and we have to go for the reduction in the reach of the distance relay, and we have to go for the relay interoperability. Likewise, we have the different challenges in the production. So when we are working with the DC microgrid, so one of the most challenges is the production. So when we are working with the microgrid with the grid connection, so we have the bidirectional power flow. So that is the one of the challenge why we are having the more production issues as well as the production challenges. So those are the production issues and production challenges, and these are the different issues of the microgrid as well as the stability issues. So I'm going to give here. So I'm going to conclude what are the different challenges, research directions. So as we can see, we have already developed the voltage and frequency control methods. However, so these methods we have to develop fully, and we have to verify all these methods with the field demonstration as well as the experimenting for both grid connected as well as the islanding mode of operation. As we can see, when we are moving towards the higher penetration of the distributed generation, and also we are going for the transition period between the grid to islanding mode of operation. So we have to minimize the transition period between the grid tied to islanding mode to grid tied operation. And for that, we have to develop the proper island detection methods, as well as we have to develop the proper control methods for taking the seamless transfer between the islanding mode as well as the grid mode of operation. So this is the one of the another challenging area where we can work. And also first one where we can work on the experimental verification of the different voltage and frequency control methods, and also field demonstration of the various voltage and frequency control methods. And also we have to focus measure on the whenever there is a occurrence of the black starting, and we have to go for the different control for the black starting control, and we have to focus on the production, we have to focus on the management, energy management, and we have to focus on the power quality and communication as well as the cyber security. And also we have to go for the more robust, novel, intelligent as well as the dynamic power delivering network by furnishing the reliable, stable, and more secure advantages. That means we have to go for the when we are going with the modification of the present era microgrid, we have to go with the more robust, novel, intelligent techniques. And also there are some other economic, reliable, and safe operation microgrid constraints like, so we have to see that, so what are the investment, and also we have to see that what is the cost of the electricity generation. Also we have to see the what is the, besides the cost of the electricity generation, we have to see the what is the cost of the storage devices. So finally, we are still at the beginning of the story, as we are in the starting. So we have to do there are many other interesting challenges. There are many interesting challenges that we must be investigated. And also we need to put a lot of the research development demonstration efforts to make the microgrid implemented practically in the practical scenarios at the distribution network. So these are the different challenges, research directions where we can work. And here I'm giving so what are the different simulation softwares tools so that can be used. So as we can see, we have the different offline simulation tools, we have the different real-time simulation tools, we have the different software-based tools, we have the different energy management tools like, as we can see, PSCAD, EMTDS. So it's mainly for the electromagnetic transient to dynamic simulations. We can also go for the MATLAB simulating that can be used for the many applications. We can go for the GAMS-based one. So it is mainly the high-level language for the mathematical optimization, as well as when we are going for the optimization problems, we can go for the GAMS software. And we also have the Transys, that is the thermal energy system specialist. It's mainly utilized when we are going for the simulation of the hybrid system, having the different energy generations like cogeneration, and we can also go for the Homer software, the Hoga software. It's mainly for the hybrid optimization for the genetic algorithm. And further, we can go for the real-time simulators in order to check for the hardware in loop simulation as well as the real-time power hardware in simulation. Like we can go with the any different types of the real-time simulators like OpenRT simulators, RSCAD RTDS simulators, or the Typhoon HAL simulators, or maybe you can go with the speed goat real-time simulators, or we can go with the any other like Plex-based real-time simulator. So based on the what type of application we are going to work for that particular application, and we can also go for the Java-based environment, different things. We can also go with the other software compatible with C, C++, Java, and Python languages like Cplex. So based on the applications, we can go with the different tools. We can go for the co-simulation of the things like we can go for the combination of the utilizing any two softwares. So based on the application, suppose when we are implementing some algorithm with some other different software, when you have the virtual power network with the real-time simulation like RSCAD, PSCAD, OpenRT. So with that case, we can go for the co-simulation of the things like software in loop simulation or the hardware in loop simulation or the power hardware in simulation. So likewise, we can develop the different types of the different control algorithms, different energy management system algorithms, and different other applications. We can verify all these things before going for the field experiments or the real-time application. So that's all about control and energy management of the microgrids, different issues and different simulation softwares. So thank you for your time. Thank you for your all the Thank you to all the participants for your patience and the time. Now I am open for the questions for the next 15 minutes.
Dear participant, you may ask the questions.
When you were explaining about the DC microgrid system, there was one disadvantage that you mentioned.
Yeah,
The disadvantage in a DC microgrid is that the small scale microgrid is basically a disadvantage. So, sir, how can you classify small scale microgrid as a disadvantage for this DC microgrid system?
No. So you understood the point in a different way. Let me go through that one. So this is what you are talking.
Yes, sir.
See, like we usually prefer the DC microgrid when we are going for the small scale implementation. So that in that point of view, we mentioned it as a if you are going for the medium scale one or the if you are going for the medium scale or the large scale one. If you see like whatever the DC microgrid, if you see the conventional AC distribution, so everything is the AC only. If you see the laptop charger, although inside we have the AC to DC converter, we have the battery of the laptop, but in what point we are connecting? We are connecting to the conventional AC distribution only. But when we are moving towards the large scale DC distribution, large scale DC microgrid, so we have to remanufacture the each and every equipment for the DC voltage only. And before that, we have to decide the what is the optimal DC bus voltage, which we can select whether it is 24 volts, 48 volts, or 220 volts. So that we have to decide. And after that, we have to suppose whatever the conventional loads we have, all are the AC points only. So we have to remanufacture all these things once we deciding the DC voltage of the particular equipment. So that is the reason we usually prefer for the small scale microgrid for the DC microgrid. But if you want to go for the medium scale, higher scale, then there is a requirement of the many DC to AC conversions, AC to DC conversions.
Yes, sir.
So in that point of view, we have mentioned that one.
In another question I have, like on the slide 78, you mentioned some objectives to minimize the cost in basically microgrid systems, like in the slide 78.
Yeah.
Yes.
Huh.
Yeah. So, sir, here, like you mentioned, like if we have that there are few points that you have mentioned, that one is the operational cost, environmental cost, and the energy storage cost is required to minimize the cost of the energy management system. So we know that in basically a microgrid, one of the most expensive component is the battery storage system. So, do you think that it is an advisable choice in the very beginning if we are setting up a microgrid to go with the diesel generator as a storage system instead of preferring a
See,
battery?
diesel generator, how you can, diesel generator can be a storage system. Diesel generator, it is only the emergency generator.
No, not the solar system. What I am trying to say is that to use it in place of the battery storage system.
No,
That's
no,
what I
see,
am
with the
trying.
diesel generator, you can supply the power, but you cannot store the excess power, na. So when we are dealing with the renewable energy resources like solar PV and wind, so sometimes you may have the more power generation from the solar PV, where you will store that more power generation from the solar PV if you are using the diesel generator. See, diesel generator also will have the very good application. Suppose when we have the SOC level of the energy storage system is below the 20%, and when we need the power, when we have the more power demand as compared to the power generation, so in that case we have to go with the switching on, and we have to go with the emergency diesel generators. But why we are not preferring the diesel generator is we are currently concentrating on the minimizing the CO2 emission, and we are moving towards more renewable integration. So that is the reason we are not preferring the emergency diesel generator, and we are preferring the energy storage instead of the emergency diesel generator.
I get it. So
Okay.
in the next slide, that is in the slide 79.
Hmm.
Yeah. So here you mentioned that in the customer side there are some sources, right? PV, wind turbine, and the conventional hydropower and diesel. So sir, here there is also EV. So basically, what you are trying to say is that we can also make use of EV as a source, right?
Yes,
This is
like
what you are.
EV, we have the grid to vehicle and vehicle to grid. So when we are considering
Yes.
the vehicle to grid, in that case also we have to consider the EV, na? So here we are talking about the vehicle to grid. If you see the
Yes, sir.
battery, if you see the battery and EV, so both if you see the grid to vehicle and vehicle to grid, so grid to vehicle means it is like a charging, and vehicle to grid means it is like discharging. Like whatever the battery we are operating, charging and discharging. So likewise, EV also will comes in that case only, grid to vehicle and vehicle to grid. So in that case, we have to include the electric vehicles also.
Yes, sir.
Yeah.
Son, one last question. Like in the slide 84, there
Hmm.
was like you mentioned about the load forecasting techniques
Hmm.
in the slide 84. Yeah,
Okay.
uh, 84. Sir, basically what you said that variables from the forecasting techniques, what we do is that we first define a model and then we do the forecasting, and then the variable that we achieve, we use it in the energy management system. So sir, I just want to ask that the basic idea what we do is that it's like that we do some, like suppose there is a solar
Okay.
photovoltaic system. So what we are doing is that we have the previous data, like what is basically the irradiance curve of this place.
Okay.
What we will do is that we will use that past data,
Hmm.
and we will like predict that what will be the nature of the irradiance in the near future, right? And so we
Okay.
will get that curve, and then from that curve what we will do is that we will get the power curve,
Hmm.
and with the help of that power curve we will use it for the optimization. This is the technique that we basically use in the forecasting
Yes,
when
yes,
it
yes.
comes to photovoltaic system.
No, it is not like a single forecasting. Like forecasting is one of the task in that. So we are using in this way. We are using the energy management.
So basically, I just want to ask is that what is the basic idea of how we do the forecasting? This is my question. Is like in the solar photovoltaic system,
See, that's
what
what
is
I
the
mentioned.
general
The
idea?
forecasting can be done in the different time frames. Short-term forecasting, medium. In one slide, I have mentioned the generation forecasting. I think this is the thing. So as here you can see, we have the different time frames, like very short term, medium term, long term. Like so, whatever the application. Suppose if you are going for the dynamic control for the renewable power generations as well as the load tracking. So in that case, we have to go for the very short term. It is not like we cannot use the whatever the historical data of the previous year. So we can use the historical data of the previous year at the tertiary level, like when we go for the economic load dispatching or load scheduling or the generation forecasting. So for that long term, we can utilize the historical data. For the short term, very short term, we cannot go with the historical data. We have to go for the real time weather monitoring and weather forecasting. You got my point?
Got it, sir. Thank you. That's it from my side. Thank you, sir.
You're welcome.
Thanks to our
Yes.
speaker.
So, on behalf of the Albag Education Institute, Agra, I would like to thank our honorable speaker today, Dr. ESN Raju, for being the honorable speaker at today's meeting and providing us a wonderful lecture on the topic of control and energy management in microgrids. Thank you very much, sir, for your time. And you gave a wonderful explanation of the question, and you also answered the wonderful explanation of the topic, and you also answered the questions that we asked. Thank you, sir, for your time. Thank you very much.
Yeah, thank you. Thank you for the opportunity involving me in this one of the good faculty development programs.
Thank you very much, Dr. Raju. On the behalf of the Airbag Education Institute, Agra, uh, please accept the e-memento from our side.
Yeah, thank you.